Hi, this is Wagner Kamakura. In this tutorial, I'm going to show you how my predictive stepwise logistic regression tool works. If you need more information about logistic regression, this will be a good time for you to watch my tutorial on logistic regression for Excel. Predictive stepwise is a process very similar to stepwise regression as you learn in your stat class or data analysis class. The difference between predictive stepwise and stepwise is that stepwise linear regression, for example, focuses on fit. You calibrate different regressions on a calibration sample, and using statistical tests, you decide which model is better. Predictive stepwise, on the other hand, focuses on predictive performance, where you calibrate the model or competing models in a calibration sample and evaluate these models in terms of their predictive performance on a holdout sample. So the focus here is on building a model that is likely to perform better in making predictions outside your calibration sample. And the process is fairly straightforward. Again, the main idea is to select predictors based on predictive performance, how the model produces predictions in a holdout sample rather than fit in a calibration sample. And the goal here is to build a model that's likely to perform well in making predictions of the unknown rather than explaining the known, explaining your calibration data. And I'm going to go over the steps in this fairly intuitive process. First step is to randomly split the sample into a proportion of holdout cases, keeping 1 minus p for calibration. If you have a sample of 1,000 observations, you reserve, let's say, p.3, 30% for holdout, and use the other 70% for calibration. Then you run one logistic regression on the calibration sample, adding one of the predictor candidates at a time to the current logistic model. So if you start from scratch, you simply run a logistic regression on the calibration sample using each one of the predictors by itself. So you're adding each one of those predictors to the current model, which is a model for nothing. Then you apply the calibrated logistic regression coefficients to the selected predictors, to the holdout sample, to make predictions of the dependent variable, and calculate the predictive likelihood of the actual events observed in the holdout sample. So you apply your calibrated regression coefficients, logistic regression coefficients, to the predictors on the holdout sample to make predictions of the dependent variable. In our logistic regression, predictions are probabilistic. So you're going to predict the likelihood that the observed event would occur. The best model then is the one that produces the highest predicted likelihood for the observed events. The next step is to compare the predictive log likelihood obtained with the addition of each predictor candidate to the current model with the predictive log likelihood of the current model. We're trying to find out what was the improvement in predictive log likelihood that you obtained by adding each one of the predictor candidates to the current model over the predicted log likelihood of the current model. If none of the predictor candidates produce an improvement in the predicted log likelihood, then the current model is the best one. You already obtained or found the best possible model. Otherwise, you add the predictor candidate that produced the highest improvement in predicted log likelihood in the holdout sample. And you keep repeating the steps 1 through 4 until the test, the comparison of the new model, adding one candidate predictor, does not improve the predicted likelihood of the current model. When you cannot improve the current model, that's your best possible model. So that's a very simple process. Let me show you graphically how this works. So here we have our sample. That's the data that we have. Then we split the sample randomly into a holdout. We take P percentage of the sample randomly as a holdout and use 1 minus P percentage of the sample for calibration. So now we have a set of candidate predictors to add to the model. We have a current model, and we are trying to find out which one of the potential new predictors should we add next. We take each one of the new predictors, add to the model, calibrate the logistic regression with this new predictor candidate added to the model, obtain the logistic regression coefficients, apply these coefficients to the predictors in the holdout sample, calculate the predicted log likelihood for each event, and sum up the predicted log likelihood for all observed events. And that sum of the predicted log likelihood of all observed events is the predicted performance of the model. And the new candidate that produces the highest predicted log likelihood is your best candidate, as long as that predicted log likelihood is better than the one that you obtained with the current model. And to improve the ability to identify new predictors, we replicate this process k times. In my tool, k can be from 1, only replicated once, to 10. Repeat this process 10 times to find the next predictor. Add that predictor to the model if it improves the predicted log likelihood. Then repeat the process again for all the remaining candidates to see whether there is any other predictor to be added. And keep going until you cannot improve the predicted log likelihood in the holdout sample. So that's pretty much the very straightforward, intuitive, predictive, stepwise process. Again, the idea is to select predictors based on holdout performance in predicting a sample that we did not touch, rather than based on fit, a sample that we touched, a sample that we used to calibrate. And the goal here is to identify the model most likely to perform well in predicting the unknown rather than explaining the known. And steps, again, are very simple. Randomly split the sample into a holdout and calibration sample. Run the logistic regression on the calibration sample, adding one predictor at a time to the current logistic model. For each one of those models where you add one predictor to the current model, you obtain the logistic regression coefficients, apply them to the predictors in the holdout sample to calculate the likelihood for the observed events in the holdout sample. The best model is the one that produces the highest predictive likelihood for the observed events. Then you compare the predicted log likelihood obtained with the addition of each predictor candidate to the performance of the current model in the holdout sample. If none of the predictor candidates produce an improvement in predicted log likelihood, you're done. You already got the best possible model. Otherwise, you add the predictor that produces the highest improvement in predicted log likelihood. And you keep repeating this process k times for k random sample. So you replicate the random split k times and calculate the performance of each one of the competing models across these k replications. And repeat these steps 1 to 4, adding predictors sequentially until you cannot improve the predictive performance of your model. Now I'm going to show how Kate, Kamakuras Analytic Tools for Excel, will do this very easily on a point and click basis for you. For this demonstration of predictive stepwise logistic regression, I'm going to use an example from Kate, Kamakuras Analytic Tools for Excel. If you open the example spreadsheet and navigate through the tabs, you're going to find a tab, Predictive Stepwise Logistic Regression. In this example, we have about 21,000 observations. These are 21,000 patients. And for each patient, we know the status of the patient as having or not having cardiovascular disease. So that's our dependent variable, whether the patient has cardiovascular disease. And as potential predictors, we are going to try to use a profile of the patient: age in days, height in centimeters, weight in kilos, systolic blood pressure, diastolic blood pressure, high cholesterol, very high cholesterol, etc., etc. So we wanted to develop a score that would predict the likelihood that a patient would have or not have cardiovascular disease. So we want to estimate a linear combination of the predictors. Not all of them, but we want to select the best ones. And the linear combination that will produce the best prediction on a holdout sample. of the likelihood that a patient would have cardiovascular disease. So for that, I go to Add-ins, Kamakuras Analytic Tools, and right here you see Predictive Stepwise Logistic Regression. And I recommend that before you run any logistic regression, that you try first to run a stepwise linear regression, just to make sure that the data does not contain errors, that the data does not contain perfectly collinear predictors. Because as I mentioned in other tutorials, Kate is very picky about data. The assumption here is that you are well versed in Excel and able to put the data in exactly the format that is required by each one of the tools. And the format is usually explained in these examples. This particular tool has a maximum of 100,000 observations, which for instructional purposes is more than enough, and 60 candidates for predictors. It already highlighted the data. If it's not highlighted, you can click here and define the range for your data. Then it's going to tell you how many observations were read, 21,118. How many predictors, 13, that you can choose from. Then it's going to ask you, do you really want to change the default parameters? And I'm going to show you that there are only two very simple default parameters. First one is the percentage of the overall sample that you want to hold for predictive validity test. Can go from 10% up to 50%. I'm going to say 50%. So I'm going to take half of the sample for calibration, half for holdout. And how many times do you want to replicate the random sampling? You can do it only once or up to 10 times. Now you have to keep in mind that logistic regression is an iterative process. Every time you try to estimate a model, it's going to take a while, especially when you have a large number of observations. So you have to be careful about how many times you want to replicate. I'm going to replicate 5 times. So right now, it's running every possible model, including each one of the 13 candidates for predictors. And it found age in days as being the best candidate, producing an average predictive likelihood of 0.51. It also shows the average predictive likelihood for the negative events, no cardiovascular disease, 0.512, and for positive response, yes, it does have cardiovascular disease, 0.516. Now we're going to try to add a new predictor. So now the tool is going to run one logistic regression that includes age in days plus each one of the candidate predictors that are still available and compare the predictive performance, average predictive likelihood, with the current model, 0.514. None of the new models, adding one predictor from the remaining candidates, if none of the models produce a better predictive likelihood in the holdout sample, then the current model is the best model. If not, it's going to add the predictor that produces the highest improvement in the average predictive likelihood. Again, it's trying running 5 different regressions, logistic regressions, adding each one of the predictors. And he found that systolic blood pressure is the best predictor to add to Asian days. So you can see that the average predictive likelihood went from 0.514 to 0.524. See if we can add another predictor. Now we went from 0.524 to 0.559, an improvement of 6.6%. See if there is any other predictor to add. Keep going. Keep going. So you can see now that the improvements in predictive fit are marginal, 0.04, 0.07%. And at this point, cannot find any additional predictor. As you recall, we had 13 candidates, and the model included 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 predictors. So it left 2 out. And we were able to predict on average each one of the events with 0.56% probability. in the holdout sample. And these are the predictors, and these are the weights that we apply to each predictor to calculate a propensity score that would allow us to identify the patient with the highest likelihood of having cardiovascular disease. So that's how the predictive stepwise logistic regression tool works. So it's a very simple, intuitive way of building a logistic regression model with the purpose of maximizing prediction in a holdout sample.